Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. Welcome back friends. In this section we shall learn how to design various connections like the base plate, the rigid moment connection, then the shear connections, then bracing connections. So this was our STAAD model which we had finalized. Now if you go to the 3D view, the 3D view looks something like this. Now this is our z-axis and this is our x-axis. So most of our columns are fixed above z-axis. So there will be movement that will be created about the z-axis and it is pinned about x-axis. So only shear force and axial force will be there when you consider the forces about z-axis, x-axis. So about z-axis, both moment, shear and axial force will be there. So there will be axial force and there will be shear force as well. So let us first see the base plate connections. So let us select all the columns. We already have defined a group for columns. So go to select by group name, columns, view, selected object. So these are our columns. We shall consider same kind of base plate for similar set of column. So let us first see what types of columns are there. So if you go to property, we see we have R10. So select by specification property R10. So we have 4 such column, 6 such column, but behavior of this column and this column will be bit different from this column. They are actually making a moment resisting frame which is resisting gravity load as well as lateral load along x direction. So we shall consider only these 4 columns. We shall not consider this column and this column. So let us have view of these columns only. So go to view selected object. So we have these 4 columns. So in my website designsteel.in, you will find various Excel sheet to design various type of connections. So I request you to download those sheets and go through those sheets. Wherever I have given a reference to the clauses of the code, even I have mentioned the page number, so please go to that page and read that particular portion of code at least. So that will provide a lot of insight to the design of connection. So that will help you to have a better grasp on connection design. So I am opening on such Excel sheet, a spreadsheet for base plate design. This is one such Excel sheet. If you see, I've given the grid location number, so we have to change this. Which should be in green color. The green field should be changed. So these are the places where the maximum axial force is there, minimum axial forces. These are the cases where the base plate has to be designed. Now I have further added one more thing so that the major direction movement is captured, because the STAAD will give maximum movement either in about X direction or Z direction depending upon the orientation of the structural model. The model could be modeling could have been done in such a way that the major direction, for some column the major direction will be about X, and for some column the major direction will be along Z. So in our cases, for these 4 columns the major direction is about Z axis. We have to provide various inputs here. This is a configuration or similar numbers of bolts, anchor bolts are there on both sides of the flange of I section, I column. We'll also see a case where there could be more bolts on the outer flange and lesser bolt on the inner flange, which actually produces some kind of eccentricity. So some additional movement will have to be considered for that. So now let us go back to the STAAD file again. For the first case, we have to select those support. First case, we have to take maximum axial force. So select this force support. Go to post processing mode. Post processing. OK. Apply and OK. So these 4 nodes are selected. If you press Shift S, the support symbols will not be seen. You can see the nodes only. If you press Shift N, the node number will be seen. Now node number 8, 9 and 12 and 14 has been selected. So go to report, support reaction. So our measure movement is about Z direction. So movement Z. Loading shall be all the limit state cases with factor loading. So our case starts from 51 to 338. So this could be the maximum movement, or at the end At the end also, in negative also it will be the maximum moment. We should see both the cases. So 32.195 is one case, and then 33.913 is the one case. This is the maximum moment case. So let us pick this up and go to the Excel file and paste it in maximum moment column. Okay. So this we leave it blank. Let us leave it blank so that we know whatever we are pasting is properly or not. So I can go to report, support reaction, sorting by y direction, loading again. (51) to 338. All this loading you have to select. You can select 51, then press Shift key and select 338. All these load pieces will be selected. So OK. So our maximum force is this one. Maximum axial compressive force is this one. So copy this and go back to so 243 kilonewton, 24.3 metric ton is the maximum axial force. So you have to see the minimum axial force case also. Copy. See, there is no uplift case here. So in this Excel sheet it will not be designed. In case there is a uplift, it will be the bolts and base plates would have been designed for tension and shear. So about local z-axis, the moments are automatically related in this sheet. Now you have to provide the next member dimension. The member dimension, you have to go back to the have to go back to the STAAD file. Let us see what is there in the STAAD file. What is the section sizes? Go to property, modeling, general, property. So R10 of the size, so 370, 005, 170, so 350 by 5 is the wave and 175, 10 is the flange. So let us go back to the STAAD file. 355 is the wave and 175 by 10 is the flange. Let us consider the grade of concrete as M25 itself. Many times we may have to go for a greater grade. So FCK will be 25 Newton per millimeter square. So bolt dia, let us try for 16 mm dia. Bolt distance is 250 to 40. Washer dimension, you will get the washer dimension from any general textbook showing any details that is showing the washer nut bolt sizes. It could be available from the net. In textbook also it is available. So then we have got gusset plates. So we are taking certain weight. See, our gazette plate will be something like this. The edge of the column. So this will be our getter height. This is our getter height, GH. This will be our smaller height, 50. This as of now we are taking is 85 mm. So if you can see 16 into 1.5 is 24 mm, but if you can go for 24 mm, so at least this should be twice of this. But again, we have to accommodate that the washer dimensions also. So 75 plus, if we leave a clearance of 5 mm on each side, so that's become 85 mm. So that is why I have taken this width as 85 mm, at least this much of width will be taken to board. If you see the board will be something like this. This will be board, or washer will come something like this. It will have nut, all that. So I will kept a clearance of 5 mm on each side, and then so dimension required is 376 and 564. We have rounded it off. Let us make it 375 mm. Breadth, so 376 mm is required. 564, so 570 is okay. Thickness, let us try with 16 mm. Base plate, real stress of base plate 345 mm, 345 Newton per millimeter square. So our maximum stress is 1.774 Newton per millimeter square. So this is the maximum case, maximum axial force. There is no tension. So tension case is not available. All these equations are available in Subramaniam. The derivation of this equation is given in steel structure by Subramaniam. So if you want to have a better understanding, either you can go through Subramaniam or any other standard textbook, but as of date, I feel it is the book by Subramaniam which is the best. Obviously, this is my personal opinion. You see, this is the case when I consider a RCC beam. In a RCC beam, tension is taken by reinforcement and compression is taken by concrete. The diagram is something like this: 0.445 FCK. So this parabolic diagram has been idealized in Subramaniam book, and this equation has been derived in his book. We are using the same equation, and done from the basic also. Further, there is no tension, so we have not considered any tension application here. So nothing is there in tension. Then base plate thickness based on compressive process. See, this is one part of gazette plate. So our I column is something like this. Base plate goes something like this. Then there are some gazette plates we have provided. Gazette plate is something like this. We have wood here, wood here, wood here, wood here, wood here. Again, this side also we have woods. So this is one of the part. This is one of the part which we are considering. So this is the part. So there is AB, and this stress has been taken from Roke's formula for stress and strain. So see, the maximum stress is 390 Newton per millimeter square, and it is asking for revision. So let us go back to the initial part itself of the Excel file and revise the base plate thickness. Let us make this base plate thickness as 20 mm. So now if we go back to here, so the maximum stress here is now 250 Newton per millimeter square, level is 330 Newton per millimeter square. So this has been considered from the tension case, and this is the case which have been considered from the this is the case for compression case. This is for compression. So next will be when there will be tension in the board. So this has been derived from the fundamentals, and the effective weight resisting A1 and A2 has been taken from AISC. So from this fundamental, whatever thickness is required to resist the tension has been arrived. Locations we have to change. So let us see what is the grid. So you see, during wind location we have wind competition. We have assigned some grid A, B, C, D. So these are the columns along grid B and along grid C and grid 1. So it will be grid 1, 1B, 1C, and 3B and 3C. So let us go back to the basic program. So we create 1B, 1C, 3B, 3C. Save it and let us close it. Now let us now open a Excel sheet that has been also given in my website, that is designsteel.in. So it's a 5-plate configuration. It's a 5-board configuration. If you see, This is the sheet. In this sheet, we have taken 5 board configuration. Now see, the boards are not symmetrical about this flange. So obviously, because of unsymmetry, some sort of moments will be created that should be considered in design. So wherever at times we can reduce the number of boards by adding little bit of movement to the design consideration. So this is the sheet we will use here. Again, let us make it blue or green. We have to change it. Let us go to the start file, view whole structure. We have these 2 columns as R10, these and these columns, view, shift S. Take the support tool, report support reaction. First, let us take maximum oil loading from 51 to 328. Okay, so 336 is the maximum load. Copy, paste. So we have to see the grid location also. Our grid is 2, grid 2. This is grid 2A and 2B. So grid 2A and 2B. Okay, you can take the minimum force also. Again, there is no tension at all, so this will not paste. Okay, then let us take the maximum movement. Select those nodes, report, support reaction, movement Z, it is our Z axis, loading. One 40 km is the maximum movement, and let us go 29 minus 29, so 40 is the governing. So let us copy it, go the Excel file, paste it here. So let us check our column sizes. Obviously, we know the column size, which is the same sizes. So 350 by 5 and 170 by 10. So this is already the linking. We have to correct it. So our X force will be this, shear Y, and Z force will be this, shear Z. This is, see, these global axes are being linked to the local axis of the member, and this should be moment Y should be this one. Torsion should be moment Y here, and moment Z, this one, and moment Y is coils moment X and torsion is this. Global Y is along the axial direction of the member, axial local axis of the member. So our member size is 350 by 5 on 75 by 10. See, you can make changes here, and I am taking 55 meter wide. So thickness will 564 to 78. So let us make it 280. 564. Let us make 575. Base plate thickness for trial 20. Let us keep it as it is 20. See here, in addition, this competition is not applicable. This below competition is applicable. Okay, tension per board, Pmax. Okay. Tension is below competition is applicable. Tension is developed. This competition case 2 tension is developed where movement is there. This is of the movement which has been developed due to eccentricity. So if you want, this is very at times you can ignore it. This is very but at times it could be considerable. So we should always check it. So if you want, you can add this to this movement. So our case 2. See, on the side of this Excel sheet, I have given a computation how the tension could be, extra moment could be calculated. So you can read that moment from the tension bolt and feed it here, and add this moment manually to this resultant moment. Otherwise, a looping problem could be created, because if you keep on adding and tension will keep on adjusting, so there will be looping problem. So you should calculate it manually. For our cases, it shall not be much greater, but at times it could be considerable. So you should actually check it. So these are all the cases. So again, Cmax and this is minus 2.143. This maximum tension now it is minus 2.143. So it is not taking. So if we make this tension value at part, this is at absolute. AB is absolute. Will get tension in the table. So for the tension also it will be calculated. So sigma max is 20 mm base plate is okay with 5 volt. Now we are using 5 volts. Other checks are also okay. Embedment length again required is 30 mm, but we should at least provide a nominal embedment length of 250 mm. That is the standard practice. So with this we complete the design of fixed base plate for resisting movement about one direction, that is base plate resisting uniaxial movement. For a I column usually base plate for uniaxial movement is designed. In this section we shall see the design of hinge base plate, and along with that we shall try to cover the design of beam column connections, that is the moment connection or rigid connection between beam and column at floor level and at eave level. Thank you.